Good afternoon. This is Francesco Tiezzo from North Carolina State University. I'm a postdoc in animal science. Today I'll teach you about the R software for statistical computing. We go through the installation of the software, the installation of the packages, uploading a dataset into R, and running a simple linear regression model. First of all, if you use Windows, copy and paste this link to your browser. This page will open, and using this link you can download the installer for R. If you're using Mac, you have to use this link and click on R package, and the installer for Mac will open. Once you have the installer, double click on it and the computer will take care of it for the installation. Once you have R installed, you can go to the folder which I shared with you, and you'll find several files into it. Data.csv is the file we use today for the analysis, and code.r is the R code that we will use for the example of the linear regression model. So just open it. The code will open in a text editor. It's a simply text file, in fact. And R will also open the R console, which is our workspace. The R console can take direct inputs. We can type down mathematical formulations and R will execute them for us. But if we have a text editor, we can simply move the cursor on the line of the code that we want to run and press Command Enter, and the text editor will automatically pass it to the console. Let's go and look at the code. Now, we need to install the package Lavan. Why? R comes with some native functions, but this won't be enough for running structural equation models. So we have to download some packages that have some specific functions for this statistical analysis. One of these packages is called Lavan, which stands for Latent Variable Analysis, and it's what we're going to download today. So just go with the cursor on the line, press Command Enter. It will take a while and you will need an internet connection in your computer, but these two lines showing up will mean that the installation of the package went successful. Once we have the package installed, it will be saved in our hard drive, and we don't have to download it every time we open R. But we have to upload the function of the packages into the memory. This can be done using the function library, like we're doing right now. Now we can use the functions. Another important thing to do is to set the working directory, which is simply the path to which we are going to use to find the files we want to upload. So just go ahead and find the path to the folder where you have the data file and copy and paste it here. And simply running the function setwd, stands for set working directory, we will tell R to go and take files from that folder. We can now upload the data in a format of a comma separated value file, CSV, and we can use the function readTable, which will read the file for us externally from R. We have to say there is an header, which are the column names on top of the file, and the separator is a comma. This function will upload the file, and we will create DT, which is actually a data frame when the information will be contained. So go ahead and run it. We can verify that we created a data frame using function class. In fact, it says it's a data frame. Look at the size of the data frame using function dim, and R tells us that we have 147 observations for 5 variables. We can take a look at the file using function add, which will print the first 6 rows of the dataset together with the header. So we have a column for the country name, column for inequality measure, column for food production, crops, food production, meat, and food security for each country. Now, for each of these variables, we can run a simple descriptive statistics. For example, the mean for food security and the standard deviation. You'll see that the mean can be rounded to 0 and the standard deviation of 1. Why is that? It was done on purpose. Before creating this dataset, I centered and scaled the variables that you see so that they will have mean equal to 0 and standard deviation equal to 1. So this is done on purpose to make the interpretation of the results from the statistical analysis easier. So we can use the function var to look at the variance of this variable. It's 1, of course. And the function ist to draw an histogram and look at the distribution of this variable. It will appear in a separate window, and we can see that the distribution is not completely normal, but it's close to. So we can analyze it with a linear Gaussian model and simply close the window. Same thing can be done with other variables, and they're all centered to 0 and scaled to 1. Or another histograms, and so on. I want to bring your attention though to the variable food production meat. As you can see, the distribution for this variable is far from being normal. Now, running a linear regression model with such a distribution might actually not be so correct, but let's take it for granted today, and we'll look at this later during the seminar in Raleigh. There can be transformations that can be done to account for this. In IntroToR, we can look at correlations between variables. For example, correlation between food security and inequality turns out to be negative, minus 0.37. And we can also do a scatter plot of the two variables, and which represent food security on the x-axis and inequality on the y-axis, and each dot will be a country. Same thing can be done with the other variables. Now, let's try to run our linear regression model. Before we do that, I want you to go back to the folder and open the image model.jpg, which actually graphically represents our model. So we will have a dependent variable, food security, our y variable, and 3 independent variables, for which we'll estimate for each one a regression coefficient, which will be A, B, and C, and this will be our model. So food security will depend on inequality, crop production, meat production, and some residual error, because the model doesn't account for all the variation of this measure. Let's go back to our code, and let's put together our model. We simply write it down. Okay, this is an example. And we use the function SCM from the package Lavan. SCM stands for Structural Equation Model. Today we will not run a structural equation model. That will be done in Raleigh in about a month. But this function can also be used for running linear regression models. So let's go ahead and do it. We create an object which is called fit.model, and using function summary of this object, results will show up. So this is to get familiar with the output from Lavan. First thing, it says that Lavan converged normal after 13 iterations. That's important, especially these two words, converge normal. Sometimes Lavan doesn't converge. We'll see that later. How many observations were used? 147. So if you remember, we had 147 rows in our dataset, so we made full use of the dataset. This information is probably not so important now because we didn't run any structural equation model, so we'll leave it for later. But we can go and look at the regression coefficients, which are reported here. So you remember we had A, B, and C as the betas for the 3 covariates, okay? And our dependent variable was food security. And so these are the estimates of these regression coefficients. Estimates is actually the beta, the regression coefficient. STDR is the standard error of this estimate. Z-value is the goodness of this estimate, which is given by the ratio of the estimate over the standard error. And P is the significance of the estimate, which stands for the probability that Z could be bigger than this value, actually the absolute value of z, could be bigger than this just by chance. Since by chance it could not be bigger, maybe it could be smaller, we can say that this is a fairly robust estimate. This is simply a p-value at the end. And so we have three different regression coefficients. We can see that the first one is negative, so it means by increasing inequality in our country you decrease food security, and it's a fairly good estimate, significant. The second estimate is not a good estimate at all, it's not significant. The third estimate is very strong, very robust, and is the one for food production meat. There is one last thing we should look at. This part here will show what is the residual variance for food security. Now we've seen that the variance for food security is 1, because we set that on purpose. So the residual variance is 0.68. This means that about 0.32 of the variance of food security was absorbed by these three covariates. And there are also other parameters for the estimate, but anyway, we should keep in mind that we wanna, with our model, reduce this value because we want less residual variance in the model and more variance to get caught by our covariates. So I encourage you all to go ahead and try to install R, run this simple code, maybe play a little bit with it, and I'll be happy to take any questions you have by either email or during our meeting in Raleigh. Thank you.